we have looked at first order logic, we have looked at the language, the syntax, we have looked at the semantics, both the meaning which is derived from interpretation based on a domain and a mapping, which is also called the interpretation mapping. And we also looked at how truth functional semantics is defined for first order logic, which is also based on the domain, because when we say that an atomic formula is going to be true, if whatever it is saying in the domain, that must be true in the domain. So, for example, if I say that Sucheta is the sister of Ambika, then in the real world that must be the case for this statement to be true, and we expect that in the real world that would be stored as a relation. So, maybe we have a relation in which all sisters are listed, and then you can just go and check up there whether that is true or not. So, it comes from the domain. Now, we want to move on to proofs, as that is our main objective in studying logic, is to how to derive the formula, or how to find a proof for the formula. And also our focus at least at the back of our mind should be that how do we automate this process essentially. So, we are looking for algorithms which will allow us to do that. So, let us begin with our good old Alice problem. Now, we have expressed it in first order logic, and as you can see, instead of saying that if Alice likes maths, then she likes algebra, we are saying if someone likes maths, then she likes algebra essentially. So, we are making a general rule. It is like simply like the other statement that we started with when we talked about first order logic, is that all men are mortal. We are saying in a way we are saying everyone who likes maths likes physics, likes algebra, and likewise if someone likes algebra and physics, then they will go to college. So, we are accepting that as a premise. Okay. So, this need not be the only true statement. So, it should not be seen as a reflection of the world outside, because even people who study political science and economics, they also go to college, and very often they do much better work than some of us who study science. But it is just to illustrate this whole idea of logic essentially. So, when we express that in first order logic, we use this universal quantifier for all x, and we say, and we are using predicates. So, that we have discussed that instead of using atomic sentences, we are using predicates, and sentences are constructed out of predicates essentially. So, likes x math is an atomic formula. It is not a sentence because it has got a variable in it, and likes x algebra is also an atomic formula. And when we put this logical connective implication between them, we get a formula which says likes x math implies likes x algebra. Once we put a universal quantifier outside it, then it becomes a sentence, because now we are saying for everyone in the domain, if x likes maths, then x likes algebra is. So, we can determine whether it is true or not. Okay. So, it may be possible that there are some people who like maths and who do not like algebra, then of course, the statement would be false, but we do not question that. We say this is the premise that has been given to you, and we are just figuring out how to express it in first order logic. So, likewise, the line number 3, it says that for all x, if x likes algebra and x likes physics, then goes to college x essentially. Remember that we introduced 2 new rules of inference in this, and the one that we are more concerned with is called universal instantiation. That is what we will use now. Okay, sometimes I mess up with spellings. What does the rule say? The rule says that if you have some universal formula for all x, and so I am just writing it in a slightly different form now. You have this formula alpha. This is the scope of the universal quantifier, the brackets, and this square brackets will signify that there is x somewhere in the formula alpha essentially. We are saying that we can replace that by alpha, and wherever there was x we replace it by a essentially. So, the simpler way that we had expressed this earlier was we had said for all x let us say p x then p a, where p is the formula that we are talking about, p is the predicate that we are talking about. This version is more general, we are simply saying alpha is a formula, it could need not be an atomic predicate, it could be a complex compound sentence essentially. So, we want to use that. This is our knowledge base that we just saw, and we can generate the proof in a manner similar to in propositional logic. So, for example, from statement 1 we use simplification and get that Alice likes maths, then we get Alice likes stories, then we get the formula that if Alice likes maths then Alice likes algebra, and this is where we have used the rule of universal instantiation, and the universally quantified formula, from that we have inferred a proposition or a sentence which is without variables, which is about Alice in particular. Now, we can infer that Alice likes algebra because we know that she likes maths, and we can also infer that she likes physics because the sentence number 4 in the knowledge base says that she likes stories or she likes physics essentially. That she does, that either she does not like stories or she likes physics. But we had said earlier that she likes stories, so we had derived that, and then from that one and this number 4, because we know she likes stories, then it must be true that she likes physics, and that is a rule of disjunctive syllogism. We infer that she likes physics. Now, we can say using conjunction that she likes algebra and she likes physics, and we can again now get an instance of the rule about people who like algebra and physics, they will go to college, and say that because Alice likes algebra and physics, she will go to college, and from 11 and 12 we get the inference that we are interested in essentially. So, there is an extra step of universal instantiation which was brought in, that was to generate the formula for which from which we could do modus ponens. Now, of course, this highlights the fact that modus ponens works when there is an exact match essentially. So, when we say that this is a antecedent likes Alice maths, then she likes physics, then it must match exactly the same pattern. So, it is like string matching, it must match perfectly essentially. That is why we could not take this and match it directly with this, because there it has an x inside and here it says Alice inside. So, the logical way to do this is to first use a use of universal instantiation, generate a Alice specific rule or implication, and then use that for modus ponens essentially. So, this is a forward chaining algorithm that we are talking about. When we say forward chaining, we mean we are going from the given facts or data towards the goal essentially. So, you see, okay, all this that has been given to me is true, then what else is true essentially. And we saw that forward chaining using these universal rules is a two-step process. First, we have to guess a rule which is applicable in the current domain. So, given the rule that p x for all x p x implies q x, we infer the rule that p a implies q a. Now, that is a question you should think about, that if you are implementing it as it is, how would you make this guess as to what should you instantiate x with essentially. But that is a problem that we often do when we kind of look ahead and say, okay, we are not talking of some arbitrary a, we are talking about some specific a. So, for example, we are talking about Alice in the problem that we saw just now, or we are talking about Socrates when we talk about mortality. So, we know of course, but as an algorithm, how do you guess? That is a question that you should ponder over. Of course, what you could do is you could try out different A's, try out different instances and see if you can derive the goal that you are interested in, but that could be a cumbersome problem, and as we will see, first order logic can be quite expensive at times. So, once we have got the instance of the rule, that is P A implies Q A, then we can apply modus ponens, because now the matching is perfect. We say P A here and we can infer Q A essentially. What we will do now is to look at something called the implicit quantifier notation that collapses the two-step inference process into one step essentially. What do we mean by implicit quantifier? Is that we will not explicitly write the quantifier. So, the quantifier is this here. So, that is what has been given to us, that for all x, P x implies Q x. But if you want to write programs to process all this stuff, then you have to represent that and make sense of that. And we have already seen that instead of using this mathematical notation, sometimes using a list like notation can be more comfortable. But even there, why do we want to represent these quantifiers and all if we can find a way to not represent them, and that is what we will do in the implicit quantifier form, where the quantifier would be implicit essentially. It would be there, it is just that we would not have written it down essentially. Okay, so, and how do we do that? What we do is we take a universally quantified variable, every universally quantified variable, and prefix it with a question mark. So, this is just a way of marking out that these variables are universally quantified. Anything which starts with a question mark is a universally quantified variable. What about if a variable is not universally quantified? It could be existentially quantified. We are talking about sentences. Remember, we are not talking of formulas which may have free variables essentially. So, in a sentence, it will be either universally, every variable would be either universally quantified or existentially quantified. And in the simplest case, we will replace existentially quantified variables which are not in the scope of any universally quantified variable with a Skolem constant. Essentially, it's just a special kind of a constant which differs from the constants that we have in our language. Remember, our language is propositional first order logic with L, which is made up of sets of predicate symbols, function symbols and constant symbols. So, this Skolem constant is not one of those, it is a new constant. So, we just find a way of inventing new names and use as constants essentially. They are called Skolem constants because of the logician Thoralf Skolem, who first gave us this idea essentially. Notice that I use the term mathematicians and logicians interchangeably. So, this is a implicit quantifier notation for the same 4 formulas that we saw when we were talking about this thing. So, you can see that in the first sentence we have replaced x by question mark x. What does this mean? That implicitly, which is not there, there is a for all x sitting outside, but we are not going to write it. We are going to simply write what we have written here and which is this formula, and we will keep it in mind that it is a universally quantified variable. When I say we will keep it in mind, that means our algorithms will keep it in mind and they would process them in an appropriate way essentially. In the second sentence there was no variable, so that does not change. In the third sentence also there was a universally quantified variable, so that has been replaced by a question mark x. In the fourth sentence there was an existentially quantified variable. Remember, we said that there exists an x such that man x and bright x, and we had said that this is the correct way of writing that some men are bright. Using an implication sign would not be correct, and you should think about that essentially. Try to negate that if you have a sentence like some men are bright, what is the negation of that? The negation of that is no, all men, or no, the negation of some men are bright is that there is no one who is bright, and there is no one who is bright is you can say that everyone is not bright, and if you were to say that, then it would be for all x man x implies not bright x. That would be correct essentially, but you try to negate this formula that we have here man x and bright x, and you will see that when you negate it you get the implication automatically. Okay. So, those are the this is the implicit quantifier form, and in the list notation that some of you may want to use when you are writing programs, it is the same thing essentially. This x gets replaced by question mark x, and x when it was existentially quantified, it gets replaced by a Skolem constant. So, the way we have invented name is we use the term sk for Skolem and put some number after that, the way people construct passwords nowadays, something 1 2 3, just invent a new one every time. Okay. So, next we want to talk of a process called substitution, and then a phenomena called unifier essentially, or of substitution which is called a unifier. So, first let us talk about the substitution. So, a substitution, and we often use these letters beta, gamma, delta, theta and so on for substitution. It is basically a pair of two things, one is a variable and the other is a value essentially. So, the substitution says that we are going to substitute the variable with whatever we have specified as the second element of the pair, which is the value we are calling it. So, a substitution theta is a collection of such pairs essentially, or a set of such pairs, each denoting the value to be substituted for the particular variable essentially. So, when we apply the substitution, let us say this theta to a formula called alpha, then the new formula becomes alpha theta. We denote it by saying that this is a formula alpha to which we have applied the substitution theta essentially. A unifier for two formulas, a substitution is simply saying that for variables I am going to substitute with something else. A unifier is comparing two formulas, and these formulas let them be alpha and beta, and a unifier for the two formulas alpha and beta is a substitution that makes the two formulas identical. When you say identical, you mean syntactically identical, that if you were to look at it, treat it as a string, then they should look the same. If that is the case, if you can find such a formula, we say that alpha unifies with beta. What will be the impact of that? The impact of that will be that alpha theta is equal to beta theta, that when you apply the substitution to both the formulas, they will become equal essentially. So, a unifier theta, if it unifies a set of formulas, that is possible, it does not have to be two formulas, it can be a set of formulas alpha 1, alpha 2 up to alpha n. If when we apply the substitution to all of them, they all become equal, and they become equal like this gamma, I think we can and we call that as a factor essentially. So, that is the notion of a unifier. A unifier is basically a collection of variable value pairs which makes two or more formulas equal. So, now we want to do away with this universal instantiation step, and what we do is we introduce this rule called modified modus ponens essentially. What does this say? It says that from alpha and gamma and from beta, you infer gamma theta. Now, the problem is that we have written alpha. Normally, what we would do is we would equate alpha and beta and match them. If they work, then we could use modus ponens. But what if they are different? We have seen, for example, we may have a universally quantified formula which is in the implicit quantifier form. So, they are not identical essentially. So, what do? We find the theta which will make them identical. So, that is a unifier for alpha and beta. So, once we can find such a unifier, then of course, we can go ahead and make the inference, but we have to be careful that we must apply this unifier or the substitution to gamma as well essentially. So, this rule modified modus ponens says that from alpha and gamma alpha implies gamma and beta, infer gamma theta, where theta is the unifier for alpha and beta, and gamma theta is the formula obtained by applying the substitution theta to gamma essentially. So, I hope that is clear. We would write this rule as follows. So, notice that the first formula here is a universal formula. There is an implicit for all x somewhere here, but it is not mentioned here, and it is not part of the code that you are writing. And the other fact is p of a essentially. So, how do we unify these two? We find this theta which says replace x with a essentially. If you replace x with say a, then you can go and make that inference. You can move from the left hand side of the antecedent to the right hand side of the antecedent, which is what we do in forward chaining, but you must use the substitution theta. So, that from q of x we apply the theta and we get q of a essentially. So, this is q, this is sorry x theta, yeah, this is q theta in some sense. So, that is the modified modus ponens rule. We will work with this one, and we will look at some more examples and look at other variations of proofs, but we will do that after a break.